Okay, so this is a recording of a couple of problems on static load analysis for complex state of stresses. I'm going to solve with you problem 27 on chapter 5, page 210, and then I'm going to solve a version of it where the force is reversed, and instead of compression we have tension. And the material is changed from an iron, which is brittle material, to ductile material, ASME 1020 annealed. But let's solve first the problem as stated in the book, problem 27. And it starts, its combination with 25, same as 26 follows. So we have a cast iron cylinder and carries an axial compressive load, and the torque load is 75,000 pounds. Torque is 20,000 pound-inch. Let's do this. Let's change from 20,000 pound-inch to a little bit of a bigger torque. So I'm going to make it instead. And I know why, because it's relatively small compared with the compressive stress. So let's make this 40. 40 pound-inch, 40,000 pound-inch. Okay, I just decided I did this problem offline, and I'm going to assume it to be 40,000 pound-inch instead of 20,000 because it's too small, and we're going to work graphically, and it's hard to position a point on the figure for this small stress. Okay, so we're going to assume the effect of stress concentrator. The weakest part of the column, this column is where the shoulder is, transition between the 4-inch diameter and the 5-inch diameter. We're given a filled radius, and we're going to account for the stress concentrators necessarily for this brittle material that is iron. Not as essential, being static loading for the associated problem, the version with 1020 annealed. And let's draw a figure first. So we're having the cylinder. Again, problem is 527, and we have the cylinder with a fillet radius and a base, and the axial load F, and then we have the torque. Let's assume the torque to go, not very clear on the, so torque, and we have F. Again, I changed it, the torque, I changed the torque to 40,000 pound-inch. Force stayed the same, 75,000 pounds. Okay. This minor diameter D is 4 inches. The bigger diameter, capital D, is 5 inches. This radius R is 0.25 inches. Okay. Let's assume x-axis to be longitudinal, y to my right, or to the right, so x. And we're interested in a stress element in the area of the shoulder. We have compressive stress sigma x, and looking at the way the torque goes, I'm sliding, I'm shearing to the left, so this will be tau xy. I intersect the x-axis, and it's in the direction of y-axis. So magnify here, the stress element looks like this. Okay, sigma x negative, tau xy. It's counterclockwise, that is negative. We need to find these two stresses. And then we need to calculate the principal stresses, and we're going to apply modified more theory for brittle material to calculate the safety factor, the design factor. So we're going to generate a figure similar to this. Numerical example for the material, rather, for this chart is the same as ours. It's stated in the problem, the ultimate strength in tension 40 ksi, ultimate strength in compression for that iron 140 ksi. So same material, but we're going to, of course, generate our own figure. Okay, so let's go to the appendices, where, let me bookmark this, where the stress concentrating charts are given. So we have the first one, stress concentration factor. It's a figure A18-1. So I have figure A appendix, that is A18-1, and this is for tensile. Same applies for compression. The two parameters on the graph are R over D. It is 0.25 over 4, the minor diameter, and that's equal to 0.0625, 0.0625, and I have diameter ratios will be 5 over 4, that's 1.25. Okay. I don't have the D over D 1.25, I have only 1.2. I have 0.04, 0.06, 0.07, 625. So I could assume that KT for axial loading, so KT caused by F is 2.2 from this figure. Arguable, but I want to expedite reading values from the chart. Some of you may slightly disagree. For torsion, chart to use is figure A18-9, and we're having the same ratios. Filled radius over minor diameter and D over D. D over D, it's 1.25 readily available. So I have 0.5, 0.04, 0.5, 625. Okay, so a bit more confidently we can assume KT due to or in torsion is 1.5. Okay, same charts also tell us how to calculate the nominal stress that gets multiplied by KT. So we can write sigma x is KT times sigma nominal, and so we have KT due to F, of course, it's 2.2. And then sigma nominal, it's F, and I have a negative force. It's compressive, so let's make it clear it's negative. So 75,000 over pi minor diameter, that's 4 power 2 over 4, okay, or radius squared, pi radius squared. Okay, so what do we have? Again, negative 2.2 times 75123 over pi over 4 is 1,3, that is 13,130 KSI. Okay, I wrote directly in KSI. Okay, and tau xy now. Tau xy, it's a negative because it rotates the element counterclockwise. So let me write that down as negative. And I have kt due to torque times tau nominal. So 1 point, and I said it's negative 1.5 times. So from the chart is T over pole section modulus. Torque is, we changed it to again 40,000 over pi diameter, minor diameter with power of 3 over 16. So 4 with power 3 over 16 is actually 4. So let's see what we have, a negative value, or counterclockwise rotation of the element. So 1.5 times 40 exponent 3 over pi over 4 equals, so I have negative 4.775 KSI. Okay, so I have the two stresses, sigma x, sigma y is 0, so sigma x, again, negative 13.13 KSI. This one is 4.775 KSI. Sigma y is 0. We're now going to, so we have sigma x, sigma y, we have the stress element. We're going to draw the Mohr circle to get the principal stress, sigma 1 and sigma 2 and sigma 3. Figure to go to, it's on page 151. And so let's see, I have the tau axis, I have the sigma axis, tau and clockwise up, sigma, and the center of the center is the sigma average. Sigma average, this is going to be sigma x plus sigma y divided by 2. Sigma y is 0. Let me write it here. Sigma y is 0. So I have negative 13.13 over 2. It's negative 13.13 divided by 2. That's 6.565 KSI. And then we have A. A is the difference between sigma x and the center of the circle. So I have negative 13.13 negative plus 6.565. Of course, we're at the middle, so it's 6.565 negative. I have a negative. And then B is going to be tau xy, which is negative, so I have 4.775 KSI. I can calculate the radius of the circle now. It's square root of a squared plus b squared. So this goes squared plus 4.775 squared equals, take the square root. So I have 8.117 ksi, the radius of the circle. Okay. All right. So we can proceed and draw the more circles. So I have sigma average here, negative 6.565. And then I have sigma x, which is negative 13.13, and then tau xy negative or b. So going to, and then this other point. So okay, here I have negative 4.775. Okay, this other point on the circle, the diagonal point is tau y, or rather sigma y and tau yx. Tau yx is negative tau xy. So the x-axis, if you want to orient the element, is this one. So this has the coordinates 0 and 4.775. That is sigma y and tau yx. So we have the mirror points also on the circle. Okay, so I have sigma 1, sigma 3, I have sigma 2. Could draw the 3D circle. So again, sigma 2 is 0. Sigma 1 would be a small positive value according to this figure, and this is sigma 3, negative value. Okay, so what is sigma 1? Sigma 1 is the center of the circle. I still have the radius on the calculator. So put it in the memory. Okay, so center of the circle, 6.565, but negative, plus the radius equals, this is 1.55 ksi. Sigma 3 is going to be the center of the circle, 6.565, negative, the radius equals, that's negative 14.68 ksi. Okay, so I do have the principal stresses found. Okay. All right, so with this, we can move to graphically implement a modify more diagram. So we need to show the boundary, and we need to show the load point and see, you know, where what's the distance between the load point and the boundary, and that'll be it. So I have to draw the boundary. Start a new sheet, and I'm going to assume 1 millimeter to be 1 ksi, because again, for the iron material that is given here, the 40 grade, let's go back to the text of the problem. So the problem states that the material is gray cast iron, so gray iron, grade 40, and ultimate strength in tension it's 40 ksi. Ultimate strength in compression is 140 ksi. Okay, so let's use this page, and we said like 40 and 40. Oop. All right, so let's go with it's wider than it's taller. So I have at 7 and at 7, and this will be the sigma 3 axis. And then I have, let's say 45, like right here. So this will be 40 ksi. Okay, so one more time I had 4.5. 4.5. I'm trying to get a, okay, I can use through transparency. Okay, so I'm at 20, measure 24, so this will be 40 ksi, and then 140 to the left. So negative 140 and negative 140. Negative 140. I'm using this as a square, and I need to go down 40 more units. Okay, and up. So I have the boundary, and I need to go to get to the shear diagonal. So this would be the shear diagonal. I don't need it, but I can represent this as a shear diagonal. Okay. And the figure closes like so. And like so. Okay. And then my square so I need to stop at 6. That was 14, and I close the graph. So this is the, what's inside is the safe zone. I need to, again, this will be sigma 3. This is the sigma 1 axis, and I need to position sigma 3 and sigma 1 on the figure. I said that 1 millimeter is 1 ksi. So sigma 3 is negative 14. Negative 14. Alright, so we'll continue recording. Took a break. And we have the boundary of the safe zone. Similar or identical, the boundary, with the example in the book. page 175, of course the load point is different. So we're going to position the load point on the figure. We have sigma 3, a negative 14.68. So we'll be in millimeters. 15 almost. Okay. So this is negative 14.68 KSI. And then we have the sigma 1 is 1, it's positive and it's 1.5, so a millimeter and a half. This is why I increased the torque, because with the previous value sigma 1 would have been half a millimeter, very difficult to show on the figure. Even 1.5 millimeters is difficult to show. So I have this as the load point. So again, 1.55 KSI, the load point, and we extend a line through the load point. So this is load point, this is failure point, and design factor N, we can get it by measuring directly on the load line. So I have maybe 15 millimeters, and then I'm reading here 107 millimeter. So 107 millimeter over 15 millimeters. More accurate is, of course, to write the equation of the line and solve the intersection. So we have a line that goes through 0 and through this point, and then we have the second line that goes through what point is this one? I have 40 and negative 40, and then here I have negative 1, rather 0 and negative 140. Okay. Another possibility is to project, so rely on this point from the graph and use the projection. So N can also be this distance over the calculated value 14.68. So let's see, if I'm to use this, it's 105.5 over 14.68, and they should be close. So 107 over 15, that's 7.13, or 105.5 over 14.68, this is 7.18619. Irrespective, this is a substantial design factor, and this is the problem as stated with, I repeat myself, with an increased double torque, just to have the figure a little bit easier to, the load point that is easier to position on the graph. Okay, let's do now the version a version of this problem where the force is reversed. So we have tension instead. Torque is the same. We keep the same orientation, torque, and force now is going to be, I had it, well, 75,000 pounds, but causes a so 527 star, causes a tensile stress. It would be the same area where the element is stressed the most, that is at the shoulder, and this is how the stress element looks like. This is tau xy, this is sigma x. For ductile material static loading, you can ignore the stress concentration factors, but let's include them to be on the safe side. And really the stresses would be the same. So stress concentration factor is does not depend on the material, so it would be the same. And of course sigma x and sigma and tau xy would be the same in magnitude. It's just that sigma x changes value, so it's going to be positive 13.13 ksi. Tau xy is going to be, I use negative, but again it's the orientation of the element that, or rather the shear stress relative to the element causing counterclockwise rotation. It tells us that this is a negative stress. So it's going to be the same value, 4.775 ksi. Now the material is SAE 1020 annealed. So we're assuming a material to be ductile. And I go at the back of the book where carbon and alloy steel are listed with their low carbon steel. That's carburized steel, carbon alloy steel, 1020 annealed. Yield strength in tension is same as compression, 43 ksi. 43 ksi. SY, it's 43 ksi. Okay. So what do we need? We need to with these new values, we need to calculate principal stresses. Mohr circle again will be different in some respect, and then we're going to apply distortion energy theory. So we need to calculate the equivalent stress. We need sigma 1, sigma 2, and sigma 3 to calculate it, and then design factor is it's going to be, you know, the limit case where sigma equals sigma over n. Okay, so Mohr circle for this new problem. As you can see, Mohr circle it's a very important concept. Make sure you practice enough to where you draw the Mohr circle diagrams correctly. So we have tau xy clockwise up, and sigma. Sigma average is going to be sigma x plus sigma y over 2. We have this calculated was negative value, now it's going to be positive 6.565 KSI. A is going to be sigma x minus sigma average, and it's going to be a positive value, that is 6.565 KSI, and B is going to be tau xy, but is negative, and is negative 4.775 KSI. Okay, and the radius of the circle, square root of a squared plus b squared, is the same, 8.117 KSI. All right, so let's draw the circle. We have the average 6.565, and we have the sigma x and tau xy goes negative, so it'll be this point, and then I have sigma y is 0, tau yx is positive, so this is 4.775 and 0. This is 13.13, and this is negative 4.775. All right, the circle passes through the mirror points. It helps. So we have sigma 1, we have sigma 2 is 0, and we have sigma 3 negative value. So let's see, sigma 1 is sigma average plus radius. And so it's actually, we had it will be sigma 3 turned positive from the previous one. 6.565 plus 8.117, 6.565 plus 8.117, this is 14.68. So it's the circle got mirrored, KSI, and sigma 3 now is going to be sigma average minus the radius, and it's going to be 1.55 KSI. Again, sigma 2 is 0. So we have sigma 1, we have sigma 3, we have sigma 2. We can calculate the equivalent stress. Von Mises stress, equation 5.9. So sigma equivalent, it's going to be, and let's not forget the sigma 2 is 0, so we have sigma 1 squared plus sigma 3 squared plus sigma 3 minus sigma 1 squared. So I'm going to just, so for sigma 2 equals 0, equivalent stress goes sigma 1 squared plus sigma 3 squared plus sigma 3 minus sigma 1 squared over 2. Alright, so sigma 1 was 14.68, sigma 3 1.55, and then sigma 3 minus sigma 1, that's twice the radius of the circle, so twice r. I have 8.117 times 2 equals, that's 16.234 squared. So again, this is 2 times r. All right, and everything divided by 2. Okay, so squared plus 1.55 squared plus 14.68 squared equals, divided by 2, equals square root. So I have 15.5 KSI equivalent stress, sigma equivalent. All right, so I have the equivalent stress. I can now calculate the design factor. So design factor, I'm looking at the equation 510, design factor N is going to be yield strength of the 1020 steel over sigma equivalent. And that's 43 over 15.5. I still have this number. I take the inverse of it times 43 equals, and this is 2.77 design factor, which for, according to the text, for static loading in general machine elements, it's acceptable. So for ductile material static loading, design machine elements under structure and static loading, design of machine elements under dynamic loading with average confidence on all data. Static structure or machine elements are dynamic loading with uncertainty about loads. Okay, so we're better than 2. This is not a structure, or could be a structure, whatever that is. We know the loads are static, so both iron and for compression, or 1020 annealed steel for tension, design factors are okay. I repeat it again, we assumed over the text of the problem twice the torque. All right, so this was it. I'm going to stop recording, and maybe you haven't seen the last part of it, so I'm going to let it run for a few seconds before, or should scan and post these on Blackboard. Okay, thank you for watching.